and thanks for joining us for tonight's TI Technology webinar hosted by Texas Instruments Australia. Tonight we are really excited to bring you The Matrix with David Tynan and Peter Flynn. My name is John Bayman and I am your host for this event. I teach mathematics to year 7 to 12 students at Lachlan Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. I'm excited to introduce our first panelist for this evening, Mr. David Tynan. Good evening, David.
Good evening, John.
I know that David has a keen interest in the role of and impact of technology in the secondary mathematics classroom, and I'm looking forward to him sharing his knowledge and his skills with us tonight. David, thank you for being with us.
You're very welcome.
And our second panelist this evening is Mr. Peter Flynn. Evening, Peter.
Hello.
Peter is a Fellow of the University of Melbourne and a T-Cubed instructor. Peter's knowledge of CAS, as in computer algebraic system, is more than any guidebook, and he is always willing to share his knowledge with others. So, Peter, thanks for joining us tonight and sharing some of what you know.
My pleasure, John.
So, without further ado, Peter, we'll pass over to you. That is fantastic. Mathematical Interlude 1, all yours, my friend.
Thanks very much, John. So I'll start off and talk about this lovely problem which I call analysing amazing simultaneous equations. I've done it in the past using equation solving such as elimination and substitution, but I've rejigged it tonight to use matrices. So the first thing we do in this activity is we actually play a game. Now I want to say that I want to go through the activity pretty much as I possibly can. It may not be possible because of time constraints to do all of this, and you may also consider that some of this might be a little bit too difficult for your clientele. If that's the case, have no dramas at all in modifying it. I mean, you may even, for this particular activity, even stop at this graphical exploration that I'm just about to go through. So let's start by playing the game. I'll be the audience and also the participant or the teacher at the same time. So we're on a graph page now, and what I'll do is I'll press menu and then I'll press 3 for graph entry edit. I'm then going to press 3 for equation templates. Then I'm going to press 1 for line, and then I'm going to press 3 for line standard. And what I'd like to do is to plot some straight lines that are in the form AX plus BY equals C. And the way that we generate coefficients of X and Y and the constant on the right-hand side is I ask the audience for coefficients of X and Y, and then I supply the constant. So I'll be the audience just for the sake of this. And so for the first one, the audience yells out, well, okay, for the coefficient of X, I'm going to have 3. Then for the coefficient of Y, they'll yell out 7. And then I'll say, okay, well, I'll choose 11 and press enter. Move the label away. And at the moment, it's a case of big fizz. We only have one straight line. There's nothing much going on. So I say to the crowd, well, let's do this again. So we press tab. We bring up the entry line again. Now this time you'll notice that it's E2. So this 2 is like a placeholder. So this is the second straight line that will be plotted. And so I ask the audience again. And so somebody will yell out, okay, let's go with 5. And then they'll increasingly become smarty bums because in the first example we just had positive integers, but then somebody is likely to offer you a negative integer. So they'll say, well, righto, let's do -1. And then I'll say, okay, well, I'll choose -7. And there's that line. We have an intersection point. Let's see what happens when we go to our third straight line. So we press tab again, we're repeating the process, and they get increasingly smarty-bummish, if that's such a word, and they'll say, well, okay, let's do something like 0.5 for the coefficient of x. Then they might yell out for the coefficient of y. Well, okay, the first one was a decimal, so let's do another decimal. Let's go negative 0.5. And then hopefully if I'm up to the task, I'll say, all right, well, I'll choose negative 1.5. Press enter. Now something's starting to happen. The three lines have met in a point. You can tell from the tick marks that it's very likely that that point of intersection is negative 1, 2, x equals negative 1, y equals 2. Then we'll say, well, let's do it again. And then what happens is the audience really tries to test you out. And often they'll go for, well, let's go for big numbers and try and stuff him up. So let's go for 5,000. They've yelled out. And then somebody jumps on the bandwagon and yells out, okay, for the coefficient of y, let's do 12,000. And then I'll say, well, stuff you, I'm up to this. I'll go with 19,000. Press enter. Oh, and unbelievable, it goes through that point again. So you challenge them and you say, well, let's do it one more time. And so far we've been dealing with, well, essentially rational numbers. So depending upon the number system knowledge of your audience, you can bet that this next one would likely involve surds or pi or e, something like that, depending upon the knowledge, as I said, of the audience. So we press tab one more time, and this time somebody's yelled out pi. Now notice there that I just typed in pi, that also works as pi. And then, well, by this stage, if the punters haven't worked out what's going on, I can jump in and offer the coefficient of y because I know what's going on. And I'll say, well, okay, let's go with pi plus 2 all multiplied by y. And then I will choose the constant on the right-hand side, and I'll say pi plus 4. Press enter. Unbelievable, it's happened again. So you play this game with the students, ensuring that your mental arithmetic is such that you're able to correctly obtain in your head the value for the constant in response to their coefficient of x and y. And then you say to the students, well, okay, what's going on? What do you notice? I mean, the mathematics classroom, most of the time students are communicating in their workbooks, but I think a really important component of the mathematics classroom is discourse. It's discussion, it's verbal discussion, and giving them a chance to reason mathematically. And so I don't mind if a student says, well, okay, they all seem to meet in a point. I mean, that's something that they've noticed. That's fantastic. While we're at it, I can also show you mechanically how we get that point of intersection before coming back to the discussion. So if we press menu, then number 8 for geometry, and then 1 for, or enter for points and lines, 3 for intersection, point or points. It's a matter of just clicking on one of the lines, then clicking on the second line, and what that does is it anchors that intersection point, and it also details the coordinates of it. Now, I'm also cognizant that we may have here users of TI-84. So far, this is the same for TI-nspire CAS and TI-nspire. You may need to make relevant modifications to this if you're using the TI-84, but I'll leave that up to you guys. So we can say, well, okay, what's going on here? Now, some bright spark might say, I know what you're doing. You're doubling the coefficient of y, and then you're subtracting the coefficient of x, and you're getting, and that's how you're getting the constant. And if somebody comes up with that, that is brilliant thinking, and that's, I'm actually not doing that, but that's a consequence of what I'm doing. What I am actually doing is I am representing the coefficients of x and y and the constant. If you look at each one of these, they are all in arithmetic sequence. They're all in arithmetic sequence. So, for example, you've got the triplet 3, 7, 11 is an arithmetic sequence with a first term of 3 and a common difference of 4. The second one, it's another arithmetic sequence triplet, first term of 5 and common difference of -6. And that's actually how I was generating it. These are a beautiful type of set of equations whereby, as I said, the coefficients of x and y and the constant are in arithmetic sequence. And so when you put the two of them together, you can say to the students, well, what do you think then? If that's true about the coefficients of x and y and the constant, what do you think, pretty much happens all the time? And hopefully you'll get them to say, well, okay, if the coefficients of x and y and the constant are in arithmetic sequence, then the line goes through -1, 2. In other words, you're getting students to conjecture, which I think is something that we need to do with our students far more than probably what we currently do. This brings us to our first mathematical interlude. I've got 3 here. Now, when I was talking about that trick of doubling the coefficient of y and then subtracting the coefficient of x, it's a consequence of the fact that A, B, and C are in arithmetic sequence. So, using the formula for a common difference, if A, B, and C are in arithmetic sequence, then, well, obviously, B minus A is equal to C minus B, which implies, therefore, that C is equal to 2B minus A. So that, if they're able to notice that trick, it's actually as a consequence of the properties of an arithmetic sequence. If I now go back to the TNS file, there's also a lovely verification to illustrate that -1, 2 satisfies this. And what we can do is we can represent the equation of a straight line in the form AX plus A plus D all multiplied by Y equals A plus 2D. So you understand that that is representing an arithmetic sequence of first term A and common difference D. And I've often showed this to teachers, and they can be a little perplexed by this, is if you multiply out or apply the distributive law to A plus D times Y, if you look at the left-hand side there on line 2, you can see that you've got a Y times D term and a 2 times D term. So if you equate coefficients, you can therefore state that Y is equal to 2. Then you can substitute Y equals 2 back into that equation, and the 2 D's on both sides cancel. Subtract 2A from both sides, you get AX equals -A. You divide both sides by A, assuming that A is non-zero, and therefore you get X equals -1. So that's a lovely verification. It's nice to be able to do it in one equation, because often students think, oh, you need 2 equations for 2 bits of information, but I think I do quite like that. Now, what's this got to do with matrices, you may ask? Well, we go back to our Inspire graphs page. The upshot of this, folks, is if we have a system of 2 equations in 2 unknowns, x and y, and in the first equation, the coefficients of x and y and the constant are in arithmetic sequence, and the same is true for the second equation, and it can be a different arithmetic sequence, then the solution set, barring any restrictions, which I'll get to in a moment, the solution set will be x equals -1, and y equals 2. Now, I've told you that result. I would unpack it and see if the students could conjecture it from leading questions that I would ask. So that's a fantastic mathematical result, one that's probably been under your noses all your lives, but you've never had the chance to sort of sit down and discover it or realise it. So it's a lovely result. And it's actually part of a wider result which can be extended to an n by n situation, so an n-dimensional situation. So if we went to the next situation, which is the 3 by 3 case, what would happen is you'd have the coefficients of x and y and z and the constant in arithmetic sequence in each of the 3 equations. They form 3 planes, and then the intersection of the 3 planes happens to be a line, of which that point there, x equals -1 and y equals 2, lies on that line. So there is something even far deeper going on than what I'm showing you here. So what we would do then now is, if you're, you could stop the activity there, not worry about matrices, and I think you've conducted something quite successfully. You could also say to the students, well, why don't you form some systems of equations that follow this rule and see if they work. So here's a sample page here where I've got 2 such linear equations, and they give you the solution set x equals -1 and y equals 2. Now with technology, what you can do is you can continually generate different cases, so you can get students to play around if they don't quite believe you. They can try a few more examples and say, well, okay, old mucker seems to know what he's talking about. So, but what we can then do is we can go on and we can look at a generalization. So this is where formality comes in, and this is where the algebra steps up a little bit. This is where having a CAS is an advantage. Non-CAS or 84 users can do this, but you'll need to do the algebra by hand. So what I'll do is go back to mathematical interlude number 3. This is more for the nspire non-CAS and 84 users. Now, what I would do with the students is I would get them to formulate these 2 equations. I'd give guidance on the parameters. So, for example, we've got M is the first term, P is the common difference in the first equation. In the second equation, N is the first term, Q is the common difference in the second equation. So, we'd have to have a chat about this. You can also scaffold this by having P equals 1 and Q equals 1, and just having arithmetic sequences with a common difference of 1. In other words, consecutive terms, consecutive integers, if you like. So what we can do is we can represent this as the matrix equation AX plus B, where A is the coefficient square matrix, X is your column matrix that contains the unknowns, and B is your column matrix which contains the right-hand side of the equations. And so therefore, we can represent this system of equations as a matrix equation. It's also important to note that the students will need to have been introduced to an inverse matrix and a determinant prior to doing this activity. So in going from AX equals B to X equals the inverse of A times B, what we're doing is we're pre-multiplying both sides by the inverse. So we can represent XY as the product of those 2 matrices there. So that's the inverse, and that's your column matrix. And the first thing you can do is you can say, well, righto, let's have a look at the determinant and look at the conditions for which the determinant is singular. And this should give us a hint as to any restrictions that may be placed on this system of equations. So when we calculate the determinant, after doing a little bit of book work and the distributive law, we get that the determinant is equal to MQ minus NQ. In other words, A is singular if MQ equals NP. In other words, we have come across a restriction that we require, or we get, x equals -1 and y equals 2, provided MQ doesn't equal MP. What I like about generalization is it allows you to seek mathematical truth, and it allows you to see these lovely results that you might not see if you're just dealing with the numerics. So let's look at now calculating the value of x. So what we're doing is we're multiplying this out, and we've actually formed the inverse here. So on the leading diagonal, the elements have swapped, and on the non-leading diagonal, the elements have changed sign. So we've got that x is going to be equal to 1 on the determinant, and then it's going to be n plus q by m plus 2p minus m plus p times n plus 2q, if I've said that right. Then what you do is you multiply it out. Anything in red cancels, a bit more bookwork. You can take out -1 as a common factor. This is such a lovely result there that the MQ minus NP cancels, and you end up with x equals -1. Similarly, we can do the same thing for y. We multiply it out using the matrices. Anything in red cancels. We end up inside that bracket there in the second last line, 2 lots of MQ minus NP. They cancels out, and you get y equals 2. A lovely, lovely result. Now that's attainable by hand, but I do understand that to do that by hand, it's quite likely that you're going to deal with an algebraically able class. If you're dealing with or using CAS, it's quite an interesting scenario. So using CAS, what we're going to do is we're going to assign matrix A. So I'm going to press A. To use the obtain the assign command, it's control symbols template. The assign command is :equals. Then to obtain the matrix, now we want this to be our 2 by 2 square, I call it coefficient matrix. What we can do is we can press the catalog, and then under tab number 5, which is our symbols template, we can move along to the 2 by 2 matrix template, press enter, and that pastes that into the calculator page. And then what we're going to do is we're going to enter in here the respective coefficients of x and y. So we have m plus p, we have n, and we have n plus q, and press enter. Now what we want to do is we want to assign our column matrix, which represents the constants on the right-hand side. We want to assign that as matrix B. So it's B, and then control symbols template for the assign command. Then we press the catalog. We go in and we find the 2 by 1 or the column matrix template. Press enter. And in here, we will type in m plus 2p, and then n plus 2q, and then press enter. And something really interesting happens when we go to calculate the inverse. We now just simply press A, and notice that it's bold and non-italicized, which means that A is being represented in this case by this matrix. We're going to raise it to the power of -1. And whenever you use CAS, you should say, or even technology in general, you say to the students, well, what do I expect to see when I press enter? And so you would expect to see, a matrix, the inverse matrix from the previous page, and you expect to see the determinant throughout, the 4 elements, or even it might even be outside that coefficient matrix. You press enter, and blimey, look what happens here. the three elements here that I'm highlighting, that's what I would expect, but I don't expect this one. This appears to be rather in a complicated form, and students could quite rightly say, flippin' heck, what is going on here? Now, this is where we can, when we're working with CAS, it's like algebra of a different flavour. This is an unexpected result. We haven't had any say in it. In other words, it's the CAS's auto-simplification that is giving us this form. But we look at it and we say, what if we were to write this with a common denominator? What might happen? Could we change the form of element A12? So let's see what happens when we do that. Have we got a common denominator command? So in you press menu, you press number 3 for algebra, number 9 for fraction tools, then look at this, we do have one. We have number 4, common denominator. And so this is like transformational algebra. It's not so much itsy-bitsy line-by-line algebra. It's the opportunity to do something quite substantial. So we go up and grab a to the -1. Let's see what happens. We press enter, and voila, we now have the inverse matrix in the form that we expected if we were to do, you know, that by hand treatment that I showed you in Mathematical Interlude 3. Then what we can do is we can verify that we always get x equals -1 and y equals 2. So we can say, well, all right, let's do a to the power of -1 multiplied by b, and press enter, and we get x equals -1 and y equals 2. I'll leave it for another day. Well, I'll leave this question for you. There's a lot of beautiful mathematical links that have been eaten up by the CAS there, and so in a way the CAS offers a bit of a deflating result. I mean, it verifies or substantiates the result, but I think going through it by hand is actually you know, quite a satisfying result, because you see where all the links occur, and you see where all the M's and N's and P's and Q's, and you see why they disappear. So that's that. I'm going to speak for another 4 more minutes and then hand over to the Oracle. So the final thing is I'm just going to give you the briefest of summaries of how to use matrices to make coded messages. David is also going to show you in a different manner. What I'm going to do is I'm going to, I've already formed a matrix product, and the matrices are called E and M. And E is what I'm calling my encoding matrix, and M is what I'm calling my message matrix, okay? So if I type in E and press enter, that's my encoding matrix. And note that the determinant of that matrix is 1. Now this also exploits properties of the inverse matrix. Now the opposite of encoding is decoding. So I've got a message which needs to be deciphered, but we've got to be able to isolate the message matrix M. The way to do that is to pre-multiply by the inverse of E. In other words, the inverse of the encoding matrix. And if I do that and press enter, that gives us, now E to the -1 by E gives us the identity, and the identity times M gives us M. So, you know, make sure you substantiate that with the students. So what was I using? I was using spaces for 0, and I was using A as 1, B is 2, all the way through to Z equals 26. So I've got GOCATS. Go the mighty cats. And on that note, I have background information for you on encoding and decoding, just like I've done there, which I'll send and will be downloaded after the webinar. But now that's it from me, and now I'm going to pass over to David.
Thanks for that, Peter. And there I was thinking that when Mum used to talk about my P's and Q's, she was talking about being polite, but now I realise that she was actually talking about matrices all along. Boom. Now, Peter, the other thing while David's loading up his screen is somebody asked, what is the exclamation mark that's on the screen that comes?
Where did that come up?
When you times the two matrices together and you got it as a with the quotient. Sorry, the before you use the denominator part.
So I'll go back
like
to
a little yellow triangle.
Oh, that's just a warning. That's telling you, hang on, you've got to be on your game here. That relates to the restriction, and often that's a, you know, when you divide, you've got to divide by a non-zero number. It's a warning.
It's like a warning message.
Yeah, it's like a warning message there. So it's saying, you know, okay, the CAS is saying, well, all right, I'm going to do this, but you just make sure that you're aware of what the consequences are when we perform that, you know, computation.
Fantastic. All right, lovely. Thank you very much for that. And
thanks very much, John.
You, David.
Okay. Thanks, Peter. Thanks, John. I'm going to do a number of things. I've probably got a little bit more than 20 minutes, so it will go a little bit fast. However, as with Peter's stuff, anything that you see here tonight will be available to the people who are attending the webinar via the files that we send to you. So more of that later. Okay, following on from Peter's encryption idea about using inverses of matrices, I had a bit of a play with trying some encryption, and it involves also a few extra commands to do with matrices. So what I'm going to do is try to just go through what this does, and you can see the possibilities in the classroom for having students generating such encryption methods, and gives us a sort of insight into the sort of thing that's possible with encryption. Okay, so an application of matrices. So the first thing to do is to define some text string, and for those that haven't used this before, you'll see there's a variable there called MSG for message, and it's assigned a dear friend of mine's name, Wayne. So Wayne has been stored in the variable message, and then the second command is to create a matrix which is going to store the message. So there is an inbuilt command which I'll just show you quickly. If you press menu matrix create, there's an option there for creating a random matrix. Okay, so that's what I've done, and I've got one row. So the first argument to randmat is the number of rows, and I want one row. And the number of columns, you can see there is 5, but rather than say 5, what I've done is say it's the number of columns is equal to the dimension, that is the length in characters, that's stored in the variable message. This random matrix is really just as a placeholder, and soon it's going to become populated with the letters W-A-Y-N-E. So the next piece, I'm going to show you something that's a little bit surprising that you can do on a calculator page. Can I just check, John, if you can hear me? Is that easily visible? I'll make it a little bit bigger. Is that okay,
yep,
John?
you can see it fine.
Okay. So on a calculator page, it's possible to write a for loop. And the reason for doing the for loop is I want to go through every character in the variable message, which is stored, which is storing the string Wayne, and I want to store each letter individually. You can see in the next line where it ends up. So this is a for loop, which is going from I from 1 to the number of characters in message in steps of 1, and changing that previously stored matrix and assigning to it. This command here is called mid. So it's basically grabbing characters from the variable called message, and it's going through in turn basically and sucking out each letter and storing it in a separate cell element of the message mat or matrix. So that's basically what's happening, and the E here in the result is just because that's the last letter it worked with. So you can sort of ignore that. So if you type out message mat, it then verifies what we were hoping that it would do. That is, that it's a 1 row, 5 column matrix with the letters stored individually. The next part of it is to change the message text into their equivalent ordinal numbers as coded for the letters, the alphabetic letters that are used. So, for example, the capital W is coded as 87. Now, that's just an inbuilt function. That's nothing to do with the encryption process. It's just the command ord, which is for the ordinal number of each character. So the variable message matrix ord is really converting all the letters in Wayne to their equivalent numerical codes. Okay, so that's done part of the process, but now we do the bit that Peter was alluding to for this story. So the encryption matrix is just a random matrix, and so this is the key to the encryption process, that you have some matrix, a square matrix, that's going to be used to hide the letters of Wayne's name in this case. So it's a square matrix, so you'll notice that in the command it assigns to encrypt mat a random matrix with the same, well, basically 5 rows and 5 columns, because that's the dimension of the message. And now we're going to use that encryption matrix to encode the message. So the message encoded is just, as Peter did before, the product of the message matrix converted to ordinal numbers multiplied by this encryption matrix. Okay, and then, just to cut the story short a bit, the last piece is to decrypt the message. And the opposite, if you like, of the ORD command is the char command, which converts an ordinal number back to the equivalent character in their alphabet set. And you notice that it's using the inverse there. So that's showing you that the encryption and the decryption. Of course, obviously, the receiver of the message, if they are to encrypt it, must know the encryption matrix and obviously some process or algorithm to complete that final step. Anyway, I just thought it was an interesting way to do a little bit of an encryption, but also use a range of commands that are related to matrices. All right, that's application number 1, and in the time I can't really do too much more about that. Okay, the second one is to do with transformation matrices. and you'll notice I've opened a file called animation, and it won't be immediately obvious. Actually, I might try to show you where this comes from. Somewhere in here, hang on a sec, there's a file called Gecko. So what I was looking for is something less boring than a square, a triangle, or a circle to show how the transformation matrices work, just for a 2x2 transformation matrix. So this Gecko, I've got the image from somewhere, and then I've traced the coordinates. You can do this, of course, by hand and then record it. I was able to do a tracing of the path around it. So I sort of clicked on every vertex that I thought was reasonable and constructed a list of X and Y values. That's possible to do with software. You can do it in Photoshop. You can do it in free software called GIMP. But basically what you're doing is tracing a path. So all of that is just to show you that, in a sec I'll get the screen back on, that it's created a very large list of X and Y values, all right, which are basically the outline of the Gecko. Okay, so we've got a list of X's and a list of Y's, and there's quite a lot of them. Okay, I'll just go to the top of this screen, and another command that's quite useful is to convert lists to matrices. In this case, what I really want to do is to get the X's and the Y's into a single matrix, and that's what we're going to show. So the first command is a list to matrix. It's available in the menus. It's also available, of course, in the catalog. So that's getting that massive list of X values, and it's converting it to a matrix. And the one there is to say I only want one element per row. So it generates quite a large list, large matrix, or column matrix, I guess. Only one column. Okay, I'll just go down to the next one, which is a similar thing for the Y. And then I want to focus on this command, which is augment. And augment is a way of getting matrices and joining them together. So in this case, it will get that first matrix and glue it to the second matrix that we've created. Now I've just done that in isolation because it's a bit of a leap on the next page. So let's jump to that now. So this is a notes page, and on the notes page you'll see the same list is there for the X values and the Y values. I've also defined a transformation matrix, which is the A, B and C, D values, and you can of course change the values of A, B and C, D to see how they impact it. The next command is really just what you saw on the previous calculator page. It's getting the list, the X val and the Y val, and it's augmenting them together to create this. In fact, I can see it there. Can you all see that, John? Can you see that? Is that a bit small, or is it all right?
No, it's fine. You can see that very clearly.
All right. So it's creating a matrix, I suppose, 2-column and many-row matrix.
And David?
Points. Yes, John.
That's a nice use of using a notes page as well. It really makes it bigger and clearer, and you sort of, I don't know, it almost feels like a computer programming screen.
Yes, yeah. I made it as small as possible so I could fit most of it in. Then the actual calculation of the, I'm sorry, I'll just jump out of that. The actual calculation here, sorry, I shouldn't click so easily, escape out of that. The new matrix will be what happens when you get the old matrix of points and post-multiply it by this transformation matrix. And the last piece of this is just listing the values. Now, of course, that's not as exciting as seeing it visually, and so I think if we go to the next screen, you'll see the gecko. It's quite a small gecko, but it's quite a lot of points. So just doing the basics of those transformation matrix, if I was to increase the value of D, you can see that that's a dilation from the x-axis. If I did an equivalence and change to the A value, you'll see that I've retained the same aspect ratio by dilating them both in the same amount. So that's one thing that you could do. The other thing that you can do is try what happens when these values are negative. So if I change the sign of A and make it -1, what will be the impact of it? So you'll see how the reflection transformation works, and it's possible, of course, to do the same thing for the D parameter as well and see another reflection. So I'll just undo those, and what I'm going to do is animate the changes to this. So if you can see what's happening here, it's changing the value in the transformation matrix of the A by incrementing it by 0.1. And it's actually simulating like it's rotating out of the page. So it's possible to do that, of course, with a bigger one, but just as an illustration of the property. Okay, so I'll stop that now. And so I just have to click in here and stop the animation. And I'll put them all back to 1. And it's not part of the course that I teach, but it is possible to consider what happens with these, the B parameter and the C parameter. So you'll notice if you change that, you get something a little bit strange happening, and it's related to shearing, which is another form of transformation. But it's not studied in my course, but it's another thing that you can do. So in summary of that part, you basically create an object, you store it as, I guess, as a set of X and Y values, and then the transformation is working on that matrix of points to generate the new ones. And it's live in here, and then the values of A, B and C, D have been passed on into this as sliders, which you can modify. So that's quite a nice application that really did require the use of matrices to make it doable and possible. There is also transformation matrices, and I'll just change, sorry, there is also rotation matrices. So if you wanted to create a transformation matrix that's related to rotation, you could make a more simple object, in this example I have, which I'm pretty sure is a square. So if I go back to here, and I'll just put this back to where it was, and just go to here, and you'll see that it's a square that's in quadrant 1, and then you're rotating this K value here, you're rotating by pi times whatever the current K value is. That's the angle of rotation clockwise. And so this property, increasing the K, is just showing you how that rotational matrix works. And obviously this can be adapted for many other purposes. Okay, so it's 10 minutes to go, so I'll move on to the next application. And I want to hark back to some solving things that Peter was talking about, and I'm not sure whether he, no, I know he didn't really reference an inbuilt matrix command called reduced row echelon form, or RF. And I'm a bit of a fan of RF because with equation solving, and I'm just using a simple example here with a 2x2 system of equations. So basically that top line highlighted there is a matrix representation of generating the solution for x plus 2y equals 3 and x plus 3y equals 6, which we know to have a unique solution. And it's x is minus 3 and y is 3 is the solution, and as shown in the result there. However, what sometimes happens with students is that they try to do that to a system of equation which either has no solution or has an infinite set of solutions. And unfortunately, all the calculator will return is an error called singular matrix, which is obviously to do with the determinant of the matrix of coefficients. Now, RF adds a little bit extra, and the second line here is basically showing, oh, I don't know why that did that, excuse me, it's a little bit large. Let me try to make that a bit better. Did that go all bloated for you?
Yes, it has.
I'll try to get it back in a better form. All right, I'm going to put it on computer view to make it a bit easier to look at. Is that better?
Great.
So that's the same system of equations solved with RF, and you have to put in the coefficient matrix and the right-hand side of the equations in the same matrix. And reduced row echelon form both will perform row and column operations to represent the same system of equations in the simplest possible way. So the result here on the right that you see, 1, 0, minus 3, 0, 1, 3, is basically saying 1 of x and no y's is equal to minus 3. No x's and 1 y is equal to 3. So that's nice and that's pretty readable. However, let's try a different set of equations. So the next one down, you'll see it says 1, 2, 3, 2, 4, 8. So that's x plus 2y equals 3 and 2x plus 4y equals 8. And maths teachers watching will immediately recognise that that will not have any solutions. However, the RF has actually picked it up. It said this reduces to x plus 2y equals 0, no problem with that. But it also then says 0x plus 0y equals 1. And that is a nonsense. And so because it's reduced to a system in which one of the equations isn't true, there really is no solution. And the third case is the infinite solution, which is represented the 1, 2, 3, 2, 4, 6 matrix, and it says the solution matrix, and it says the solution is x plus 2y equals 3, and it has no more information to give you. So basically all the solutions will end up in that first equation, and so you have two variables, one equation, and obviously then an infinite set of solutions. That's another nice inbuilt matrix feature that is useful in that respect. All right, in the time that I've got, I'll show you one other quick thing that's an inbuilt matrix thing, but it doesn't say that it's for matrices, obviously, and it's not representing very well here, but I'll just put it back on the computer thing. So if that function, that command is for generating an amortization table, and without going into all the different parameters there, it will generate a matrix which shows the what happens, the balance of the account after a number of payments, and including consideration of premium and interest calculations. So even though you're not really asking for a matrix, that is the suitable representation in this case. I want to finish with something that's not my work, and it's a calculator file called Matrices demo, and it's actually been done by Sanjeev, and it's a whole collection of calculations that demonstrate properties of matrices and some of the commands that you can use to generate and work with matrices. Now, don't worry if you don't understand exactly where it's going, because here's something Sanjeev prepared earlier. If I can get it up and showing. Okay, so I'll just make this a little bit bigger. If you can see there, so Sanjeev is a T3 instructor, and I went to a PD last year, and he quite kindly allowed me to show this. It's a 22-page Word document which goes through a number of parts on applications of matrices in senior maths courses. This is the Word document. It refers to the file I just showed you before, and the numbering system is the same. So, for example, the final application in the 1 minute I have is if I do dominance matrix. I think I can find dominance matrix. So this is a directed graph or a digraph demonstrating, for example, 4 people playing a round robin tournament, who beats who. It's an application of networks in matrix form, and you can generate a dominance matrix which says who beat who. If you think A, B, C, D, and the matrix is representing who won each contest. And then the application that Sanjeev goes on to explain is about how you can use dominance matrices and first order and second order in order to establish a more accurate picture of who was dominant. So there are many other applications, and this Sanjeev's kindly allowed us to make this one available to you as well, so that'll be a file that you can download and have a muck around with yourself. And without further ado, I think I might now transfer over to young John.
Thank you, Peter. Sorry, thank you, David. That was fantastic. And I think that nice mention of the RF function is a really useful one. I was thinking that I've used that with my classes in the past, where rather than working out a calculation and then sort of seeing the understanding whether it's got infinite solutions or no solutions, doing it that way and getting them to think about, well, why is it giving these answers, and what do these answers actually mean in terms of the values or the the unknowns.
Yes, it is excellent. I use it as well in year 10 and 11.
Yeah, it's great, and that'd be great to have that document from Sanjeev available for people to download as well. So yeah, like you said, that'll be on the on-demand page, but also links on the YouTube channel. So thank you very much thanks Sanjeev for sharing that with us. Okay, so we're going to start wrapping things up now. So if you have any last-minute questions, please try and get those asked, as I know that David and Peter will endeavour to answer them or add them to the planning of future webinars. And when you leave the webinar tonight, a brief survey will automatically appear here in your browser. Your feedback guides us as we plan future online events. We do listen to your feedback, and so we hope you do share your thoughts in a post-webinar survey. Most importantly, your certificate of attendance will be emailed to you in the next 48 hours, along with a link to, as we mentioned already, the on-demand and YouTube version of the recordings, as well as the documents that both David and Peter have shared tonight. After we leave tonight, if you do want some post-webinar follow-up, please feel free to phone or email TI Australia on the numbers on your screen now, or the email address. I know that they'd love to hear from you, and if they cannot answer your question in the main office, then they'll get in touch with one of us as trainers. As David said, and I agree that we're all teachers who are using this technology. We see how it applies in the classroom, and we're more than willing to share our knowledge with you. And that brings us, I'm sorry to say, to the end of tonight's webinar. Thank you very much, David and Peter, for everything you've shared with us tonight.
Thank you.
Thank you.
Yeah, I've really appreciated it, and I know from the comments that people have said on the chat window that they've also appreciated everything you said and learned a lot. So thank you also, everyone, for watching tonight. Without your wanting to learn new things, not only is there no much point in us presenting these, but also Your students aren't learning new things in the classroom, and so thank you very much for you spending the last hour with us and looking to improve your skills so that you can pass it on to the betterment of our students. And on that note, I will say good night and thank you very much. Safe teaching.